let's begin with the summary of the previous lecture. In the previous lecture, I started to consider something different from the quantum computing, and then it was called as quantum cryptography. And then the more descriptive name for quantum cryptography is probably the quantum key distribution. And then in this case, and then we also simply call it as a QKD. And then I mentioned that there are two types of cryptography system, and one is called as a public key system, and which is frequently used nowadays. And another type of the key cryptography system is called as a symmetric key system. And then most of the quantum cryptography uses the symmetric key system. And then the most representative protocol used in the QKD is something called as BB84. And then, yeah, of course, this is also the symmetric cryptography system. And then I explained how this BB84 works. And then if you think about it carefully, then you will realize that the main reason this works is because of the no cloning theorem, and then the ambiguity coming from the non-commuting measurement operators. And then this sometimes also referred as the uncertainty principle of the quantum mechanics. And then if you remember that if some eavesdropper is trying to intercept or measure the eavesdrop the transmission of the single photon in the middle, then the typical situation is that the eavesdropper by herself also has the ambiguity in the measurement, and then and when the eavesdropper try to hide her existence and then retransmit the detected retransmit the photon which resembles her measurement result, then there will be always some error happening with from the side of the receiver or Bob. And then when Alice and Bob compares their measurement result, they can tell when during which interval the eavesdropper were working, and then they can just drop the entire generated key during that interval. Some people might also ask, whenever I describe such kind of situation, some people also ask, what happens if the eavesdropper keeps listening or keeps um, eavesdropping? Then and in that case, BB84 will continue to generate some error. And then in that case, you might say that, well, then the distribution of the key is not possible anymore. And that is kind of true, but that is a little bit different domain of the problem. Even for the typical communication system, you will always have such kind of problem, because if your if your enemy want to disconnect your disturb your communication, for the wireless communication, they can use the jamming, or for the wired communication, they can just cut the wire. So yeah, and then that is complete. And then even for the distribution of the secret key, then the fact that we can figure out whether there is eavesdropper or not, and then the fact that they can continue to disturb the distribution is a different problem. And then I also mentioned that there is concept of post-quantum cryptography, and then I mentioned that the meaning of the post is not next generation of quantum cryptography compared to the QKD, but here post-quantum means that post-quantum computing. So once the quantum computing, so this quantum means the quantum computing. So once the quantum computing becomes available, all the current um, uh, um, all the current cryptography system will fail. So in preparation for such kind of time, people started to develop new type of or new generation of the cryptography, and then that is called as post-quantum cryptography. So and in principle, QKD by itself also can be considered as the post-quantum cryptography because um, even with the quantum computer, we cannot break the security system from based on the quantum cryptography. And then, but for most of the case, people who are active in the research of the post-quantum cryptography might not consider the QKD as the post-quantum cryptography because generally, yeah, when people are talking about the post-quantum cryptography, they are talking about some um, a cryptography system based on some difficult mathematical problem. But in the larger sense, I think yeah, QKD should be also considered as a post-quantum cryptography. Today, we are going to introduce a little bit different types of quantum key distribution. Especially, I will be talking about QKD based on entanglement. And then why do we need such kind of new type of the QKD? Well, let's see the problem of transmission of the single photon in an optical fiber. Um, in the classical communication, when we want to transmit just the 0110, then all you have to do is send some strong signal, and then yeah, there will be no problem in receiver detecting the correct value. So all the entire information will be properly transmitted. And even if there is any problem, then there is a well defined error correction protocol so that people can just request resend resend the missing bit or some other techniques. So um, whenever you are doing any kind of communication, you are not worried that some of your information will be lost in the middle. The problem, the situation with the single photon in an optical fiber is not that case. So let's say that yeah, we encoded our BB80, one of the polarization state for the BB84, and then send it through the optical fiber. The problem is by the time it arrives at the other end, um, sometimes if the length of the optical fiber is long enough, or the distance in the free space is already long enough, then there is a lot of chance that the single photon will be absorbed inside the medium. Yeah, as you can see here, this is the schematic of the optical fiber, and then you actually can see some of the fluorescence coming out of here, which means that this thing, some of the photon passing through this optical fiber actually observed, and then it is coming out in the form of the fluorescence. So that is a very serious problem with the QKD, and then there is always a kind of distance limitation um, um, with the basic QKD system, so or a BB84 system. So what people does nowadays, they are yeah. So the length limit for the typical QKD basic QKD system is order of 100 km, and then yeah, depending on some improvement, it might be increased by factor of 2 or something. But then there is also some kind of fundamental limit because as the length of the optical fiber gets longer and longer, then the probability of being observed increases exponentially. So if even if you send a lot of single photons, and then at the end you might say that some of the photon might arrive there, but the problem is by the time when the single photon arrives, then the rate of arrival of that single photon is, or probability of that single photon arrival is too low, extremely low. So yeah, there will be always some kind of a small amount of noise, and then you cannot tell whether the signal came from the detection of occasional single photon or due to the background noise. Yeah, so yeah, in practical purpose, there is some kind of a distance limitation, but for the security purpose, we frequently need to send send that key distribution for longer distance. So what people have are using is kind of compromise. So let's assume that we have some multiple node, and then they are separate by order of kilometer, 100 kilometer. And then what you do is send the single photon from here to here, and then at here you convert, you actually detect a single photon state. Yeah, so by the time this single photon is measured, then the superposition state actually collapses, and then you will have some definite state, and then somehow, yeah, you will also send another photon, and then they will also create an additional key. Yeah, so there will be one pair of key. Yeah, let's say, or I can say that some sequence here, 1010, and then they will the other side will have the same sequence, and then between here and between, yeah. So if I say A, B, C node, and then these sequence are the shared secret key between A and B, but by using an additional QKD system, you can also create another sequence of the 0010, and then once they are shared between these two nodes, then what you can do is combine these two values together, and then, yeah, create the entire overall secret key between A and C. The problem with this kind of system is that that combination at this node is the process. It is done in the classical device. So yeah, there is actually no more quantum advantage in by using this one. And then still, yeah, because there is due to that distance limitation, yeah, people, many of the communication company um, uses this method, and this method is called as a trusted repeater. And then a repeater means that when you have some a distance limit, then the signal will be repeated, and then will retransmitted. But then that such kind of situation is similar to the problem of the eavesdropping. So there is no more quantumness in the once we use this kind of a trusted repeater. And then yeah, yeah, but yeah, again, yeah, due to the technical limitation, currently this is what people are using. But there is actually a nice solution compared to that one, and that is by using the entangled state. And then I will um, give you an homework working on this part. But yeah, you remember that we can use the entangled state to teleport some superposed state. And then if you extend such kind of concept, then you can even extend the entangled state. And then, yeah, what that means is that if we have some two node which is entangled, and then there will be additional qubit, and then this qubit will be also entangled. And then here, yeah, we have some kind of node, and this is another node. And then by doing some by measuring these two qubit at the common node, and then measure them in terms of the Bell basis, then after we do some Bell base measurement, then the state of these two qubits will become definite, but the remaining these two qubits will be eventually get entangled with each other. And this kind of um, method is called as entanglement swapping. And by repeating this entanglement swapping, you can actually extend the entangled state to a very long distance. And then, even though the generation of the entangled state, the elementary entangled state also has a similar distance limitation, but because of the entanglement swapping, we can extend the global entangled state. The length of the overall entangled state can be extended as much as we want. And then, yeah, of course, such kind of technology is currently being developed. So it takes a while until we can commercialize such kind of system, such kind of function. But in principle, if you, as you learned about quantum teleportation, such kind of situation is possible. So I will just assume that we can create some long distance entangled state. Then, there are a few different ways to implement the QKD system using the entangled state. But let's just think about some simple way to implement the PBA for using the entangled pair, because one of the property of this kind of pair state or the entangled state is that once we measure the polarization of the it, well, yeah if let me say that if I have a entangled photon pair generator like this one, and then this will generate two photons, and then these two photons will be in an entangled state like this one, then we know that if we measure this photon in some kind of basis, and then if we use the same measurement basis for B, then their measurement result will be always anti-correlated to each other. So um, if we consider only this, if we consider this part as a single system, then what we can do is we can implement what happens with the sending the single photon in the BB84, because we know that once we depending on what kind of measurement device what kind of measurement basis we used for Alice, and then let's say that I use the HV basis, then if I measure the value of A along the horizontal um, polarization, that means that B will be in the vertical polarization. And if I measure the vertical polarization for the Alice, then B will be the photon in the B, or the qubit on the B side will be horizontally polarized. And then that's not the only option, but if we measure the polarization of this photon in along the um, TA basis, then the and if I measure the polarization of the A along the T diagonal vector, that means that um, the qubit on the on the B side will be anti-correlated along this direction. So um, in principle, by measuring the A photon in random basis between horizontal and then vertical polarization. Sorry, um, random basis between the HEV basis and then TA basis, the corresponding at that time the corresponding photon will be in an orthogonal basis, orthogonal vectors. So it is equivalent to sending this photon in out of 4 possible cases. And here, one of the additional we are so such kind of situation can happen for over a very long distance. So instead of trying to send out a single photon, once we created this kind of entangled state, then we can use the same effect of the QKD, but there is no distance limitation. And moreover, we can also make the generation of this random state more naturally, because as I mentioned, if we choose the measurement basis like for between the HV basis and then TA basis, the value of transmitting if you remember when we are transmitting some photon for the QK BB84, then what we had to do is first decide the basis, and then second we have to decide what value we will transmit, meaning that we should randomly choose between 0 and 1, so that each of the encoded value will be random, so that the eavesdropper cannot guess um, for the sequence. And then in this case, we don't need to use any of the random number generator. Yeah, so previously to implement the BB84, we need some random number generator. But here, if we just use the HV basis to measure the Alice A photon, then because we cannot control whether this photon will be detected as H or V. So it is kind of random. It will be it is randomly decided, and then that decision will directly affect the polarization of this B photon. And moreover, yeah, I said that we should still decide randomly between the HV basis and then and TA basis. And then in the BB84, typically what we do is we use some random number generator to decide which basis we will use. However, if we use this kind of entangled photon pair generator, and then what we can do is, even for the selection of the measurement basis, we can do it naturally, or we can use the quantum property, um, and then it can be done by sending this photon through something called as a 50-50 beam splitter. You are familiar with the concept of the polarization beam splitter, because that's how we can measure the polarization of the photon. Yeah, so typically, if we have this kind of polarization beam splitter, then the horizontally polarized light will go through here, while the vertically polarized light will go through here. So by just measuring the transmitted or reflected, by detecting the transmitted light or the transmitted photon or the reflected photon, we can tell which which polarization that photon currently have. And then what we can do is, but yeah, this beam splitter is different types. So this beam splitter does not depend on the polarization of the input, but we say that it is 50-50 beam splitter, meaning that when any photon comes in, then there is a 50% of chance to be transmitted, and then 50% of chance to be reflected. So and this kind of beam splitter, you can consider this kind of beam splitter as a some kind of partial mirror. Yeah, so partial mirror means that when you see some of the mirror, then if you look carefully, then you can generally see the image of the other side as well. Yeah, so yeah, such kind of mirror are available. And we especially choose some beam splitter which will exactly transmit only half of them, and then reflect half of them. So if we use this kind of device, then the incoming photon like A will have a 50% of chance to be go here and detected using the HV basis, or it will be reflected to here. And then for here, I intentionally rotate this polarization beam splitter by 45 degree. Then if this is tilted by 45 degree, then what it does is actually measuring in the TA basis rather than HV basis. So our purpose is automatically implemented in on the Alice's side, and then we would also have the similar setup for the Bob side, and then because in the on the Bob side, yeah, Bob should also decide which measurement basis he will use, and then if he has this kind of measurement device, then the selection of the basis will be totally random according to the quantum mechanics. And then even after they are being transmitted, then we can decide we can detect whether this B photon is horizontal or vertical, or the diagonal or anti-diagonal. So that's one way to implement the QKD for with the entangled state. But this is a similar fashion to the VB84. And then there is another way we can also implement the QKD using the entangled state. Before we discuss the more details about the protocol, let me go back to our previous discussion about the third postulate of the quantum mechanics. Yeah, while I was explaining about the measurement in the quantum mechanics, there are more than one theory which some group of people believe, and then the most the typical theory we believe is called as the um, Copenhagen interpretation. But there was also another group of people who believe in the local hidden variable theory. And then the idea behind the local hidden variable theory is that um, the quantum state is already predetermined in advance. However, the reason we look like whenever we see some randomness in the measurement is because we don't know the entire information, and then so maybe the quantum state by itself has multiple very high dimensional information, but people can only access some of the limited dimension information in the limited dimensions. So that's why it might look somehow random. But if we know the entire information, then we can actually predict everything in the everything about the measurement result. So how can we determine which theory is correct? So that's the yes that is what John Stuart Bell wanted to figure out, and then he proposed a very interesting experiment. So he said he basically assumed that if we can design a single type of experiment which can be applied to both the hidden variable theory case and then the Copenhagen interpretation case, and then because then the model, the hidden variable theory model and the Copenhagen interpretation model are different. So the result of the measurement will be also different. So based on the final experimental result, we can decide which theory is more plausible. So that's the idea behind the Bell's inequality, something called as a Bell's inequality. And then, yeah, let me give you some more concrete idea. So let's assume that there is some person called Charlie, and then the job of the Charlie is to generate a pair of photons, and then send one of them to Alice and another one to Bob. And then what Alice does is she can measure this the polarization of this photon either by using HV basis, or she can tilt this axis by 45 degree, and then she might measure along the 45-degree basis. Then what happens to the Bob? Yeah, he can also choose two different types of bases, but yeah, the basis he can choose is either yeah, with respect to the horizontal base angle, he can either use 3 uh, 3 pi 3 pi over 8, or more likely a closer one, which is only the pi over 8 angle. So Bob can choose either of these bases, and then Alice can either choose the 45-degree or the HV basis. And then the point is they won't know, each of them decide which basis she will or he will measure um, for yeah. So yeah, at each time, yeah, they can randomly choose the basis. So there is no reason why Alice and Bob will use the same type of basis, and then even angles are different. So, and then once she or he measures some photon, and then if we have some transmission, so for this polarizer, if she measures some kind of click, that means that it is horizontally polarized. And then if she does not measure any photon in the transmitted line, then that means that the photon the polarization is vertical if she was using the HV basis. And then of course if she tilted by 45 degree, then the transmitted light will be plus 45 degree, while the other one when she does not measure any other photon, then means that the polarization is collapsed to minus 45 degree or something like that. Yeah, so um, that's what she does. And then similarly, Bob will also measure whether some photon was transmitted or it was absorbed by the polarizer. So, and then whenever she measures the transmitted light, then she will say that, oh, my measurement result is +1. While if she does not measure any photon, then she will declare that I measured -1. And similarly for Bob, yeah, whenever he measures the transmitted light, he will declare +1, while he does not measure, and then he will declare -1. So the situation is that, yeah, and then yeah, this kind of measurement, and then uh, they will repeat the same type of measurement over and over many times. And then in that case, you might get some kind of statistics in terms of the measurement result. And then what Bell suggested was if you try to calculate some kind of statistics, then for the hidden variable case or the classical case, there will be some maximum number such kind of statistics value can have. And then so because it has some maximum number, so it can be, yeah, so if we can write down some kind of expression, then this can be expressed like it should be smaller than number 2, for example. So this is why it is called as Bell's inequality, because it is a form of the inequality form. And then um, what the um, what the people who believes in the Copenhagen interpretation should should find out the case when this inequality can be violated, meaning that this calculation can be larger than 2. Then if people can create some kind of special quantum state like this one, and then if you calculate what is the expected value, or if you actually does the experiment, then you can obtain some value which is larger than 2. Then you can disprove that the local or prove that the local hidden variable theory is not correct. Yeah, so that's what I'm going to explain. Yeah, so yeah, in the next page, I will explain how this expression can be calculated or how this expression is defined. Actually, there are different types of Peirce inequality form, and then one of the popular form is something called the CHSH measurement, or yeah, it is just an acronym for the four people's name who came up with the idea about that such kind of inequality. And then yeah, from now on for the next few pages, I will simply assume that the local hidden variable theory is correct, and then yeah, based on that assumption, we will define four different types of measurement, and then so as I mentioned, yeah, at least we will assume that Alice can measure either along HV basis, or she can turn this angle, and then yeah, she can measure along 40 between along the plus minus or 45-degree basis, and then for two cases, I can describe using this kind of definition. So I will assume that alpha can be either 0 or 45-degree or pi over 4. And then I will call the case when Alice uses alpha equals 0, then I will say that Alice's measured value is represented by Q variable, while if Alice uses alpha equals pi over 4, then I will use the variable R, and then R means that the measurement result when Alice tilted her measurement device by 45-degree. And similarly for Bob, I mentioned that the Bob's, so the definition of the beta angle is the same as the Alice's case. But for Bob case, he can choose only these two angles for beta. And then one is pi over 8, and then the other is 3 pi over 8. So yeah, he can choose between these two angles. And then whenever he chooses the angle of beta angle of pi over 8, then the measurement result will be called as S, while for this angle choice, the measurement result will be represented by T. And then, as I mentioned before, Alice's choice between the Q and R basis, and then the Bob's choice between the S and T basis or T type of the choice is completely random. So for each of the trial, they can choose randomly between S and R for the Q and R for the Alice side, and then the S and T side on on the Bob side. And what we actually want to calculate is the average value whenever for each of the trial, Alice will obtain either so yeah, she can try with the depending on what so in principle she can choose between Q and R basis, but for each of the choice she will also obtain either plus value or a plus one value or minus one value. Similarly for the above, he can choose he can randomly choose between S and T basis, and then for each of the choice, he will measure either plus one or minus one, and then for so each of the measurement result is represented by this small a and small b, and then we can multiply those two values together, and then we want to calculate the expectation value. So for more concrete example, let's assume that Alice chose the R basis, and then for this specific trial, she measured plus one for R basis, and then at that trial, Bob just happened to decide to measure S basis, measure along the S basis, and then at that time he obtained the value of minus one. So in this case, I will just write down that R equals +1 while S equals -1. Of course, in this case, because Alice choose only R basis, so there is no value for Q or no value for T for Bob's case. Anyway, yeah, so for this specific trial, they obtain these values. So in principle, we can calculate the product of these two values. And then in this case, we will obtain -1. And then that was this value was the one specific case. And then because we will randomly choose the between Q and R, there is no guarantee that in the next trial we will choose the Q. But let's assume that we repeat several times, and the next time we will also Alice will randomly choose R, and Bob will choose S simultaneously. In that case, you might also obtain another value, maybe +1 again, or maybe a +1 for this S, and then this value will be +1. And then if we collect all the cases when the Alice chooses R and then Bob chooses S, then we will have some kind of +1 or ±1 value randomly appearing. And then in principle, we can calculate the expectation value or the average for that case. So that's how this expectation of R times S is defined. So if I give you more detailed example, then first, we still continue to assume that hidden variable theory is correct. So in principle, Charlie can determine the hidden variable for each of the trial. So each of the line corresponds to each of the trial. And then for the first trial, let's assume that Charlie chose +1, -1, -1, +1 for QRST hidden variables. However, Alice and Bob does not know this information in advance, and then Alice will randomly choose between Q and R, and then for the first trial, she just decided the Q. She decided to measure Q along the Q basis, while Bob decided to measure the first trial with the S basis. And for each of the choice, Alice obtained +1 and then Bob obtained -1. So in this case, we can say that the product of QS is -1. For the second trial, Charlie again randomly choose the QRST value like this one. And then we know that all the possible combination of QRST values are 16 because there are only two choices for each of the QRST. So, and then in this case, still Alice and Bob does not know this value in advance. So Alice this time decided to choose, decided to measure, choose to measure in the R basis, and then she obtained -1. And Bob also randomly choose to measure along the S basis, and then in that specific case, he measured the +1. So in this case, we only have the measurement value of R and S only, so we can calculate the product of these two values, and then we will obtain -1. And we will continue like this one. Yeah, so this is a table of the some special measurement, and then yeah, these each of the value can be always changed depending on the new trial. And then from this kind of, yeah, so assume that we try this one a lot of time. Let's say maybe n is 100 or maybe 1,000 or whatever. So we repeated this kind of experiment or trial so many times. So now we can talk about some kind of expectation value. So what is the expectation value of product of Q and S? Well, yeah, so to calculate the expectation value, or then what we have to do is collect all the cases when we had the value for the QS. So yeah, in this case, I had a -1, and then for this case, I had a +1, and yeah, there will be also non-zero cases for occasionally. So if I add all of them together, then what I have to do is also divide all entire numbers by the number of the values by the number of these samples. So I will simply assume that we try these test so many times. So on average, for the QS case, we will have and we will at least have roughly n. So this is kind of um, a formula for the expectation value. So if I just zoom in to how we obtained -1 in this case, it actually came from this first trial. And then in the first trial, even though Alice and Bob didn't know in advance, Charlie already determined this kind of combination for QRST. And then for this +1, yeah, it actually came from this fourth trial. And then in this case, QRST combination is different from this one. And then yeah, for each of the non-zero case, yeah, we can trace back to where it came from. And then yeah, I can just do things like this. Then what about the and then in this case, we know that the combination of these trial are the total number of the trial different combination is 16. So there will be a lot of repeating cases. And then in that case, even though we had the same QRS combination, yeah, in that case, we will have the definite value for Q and then definite value for S. So in principle, this summation is the summation of 16 different combination for QRST. And then in principle, because we are assuming that we are trying so many times, so on average, we can say that for each of the combination, there is some probability of having such kind of combination. And then the expectation value can be either by collecting all the values like this one and then divide by the number of all the samples, or we can just simply say that because we know the probability of each of the combination, then for each of the combination we know the value of Q and Q times S. So we can just calculate this value to find out the expectation value. So what about the expectation value for the product of Q and QT? So in this case, we also know that yeah, we have a non-zero value for QT for this third trial, or we will also have some non-zero value at some point at somewhere like 80 80 seconds trial. So if I investigate where how this value was obtained, then I can also go back to the combination of this value, and then I can say that this value came from the QRST combination like this one. And then what about this one? This one, this +1 came from this line. And then this line had the QRST value of +1, -1, -1, +1, which is the same as the first case. So I can claim that the same combination of QRST will be used for both QS expectation value and QT expectation value. And then the reason, yes, sometimes it went to here, while for this case it went to here, is because Alice and Bob randomly chooses their measurement basis. So yet along that line, yet we will also obtain the expectation value for the QT product, and then again we can also rewrite this expectation value in terms of the probability of each of the combinations, each of these 16 combination, and then we have to multiply the value of QT based on each of the combination. Then then in principle, yeah, not only for QS or QT case, we can also calculate the expectation value for RS and the RT, and then each of the expectation formula will be expressed in this form. And then what we are and now we define some parameter called as S, And then S is defined in this way. So we note that there is minus sign here. And then now I can plug in all these formula for here. So I just replaced each of the expectation with this sigma expression. And now what I'm going to claim is that we know that for each of the for some specific combination of QRST, like +1, -1, and +1, whether we are talking about QS or QT, yeah, like this one, the probability of having +1, -1, -1, +1 are the same, because that probability is determined by the Charlie or the hidden variables. So Charlie just randomly choose 16 possible combination, randomly choose 1 out of 16 possible combinations. And then the reason sometimes the measurement, that case is used, is involved in the QS, or sometimes it is involved in the QT, is because Alice and Bob randomly chooses their measurement. So in terms of the probability, they should be the same value for the same combination. Like this case, whether it was involved in this calculation or this calculation, the probability of probability of QRST will be this value should be the same. And then that same argument can be applied to all the other terms. So in other words, we can collect the entire, we can combine all the summation and then collect them in terms of the different combinations. So for 16 different combinations, there will be 16 probabilities. And then for each of the probability, we can consider this kind of um, expression. And now we also rewrite this expression by combining, by factoring out S and T for these cases. And now what I'm going to claim is this expression, this expression can be either only +2 or -2. Why is that? Because I said that Q and R can be either +2 or -1. And then let's assume that they are same, like +1 +1 or -1 -1. In that case, we know that R minus Q should be 0. So the second term will be 0. What happens if they are different? Like one of them is +1 and the other one is -1. In that case, Q plus R should be 0. While so the first term will be 0, while the second term is not. So then what we know is that whenever, and then again, if we have the same value, then same value of Q and R, then I said the second term is 0, but the first term, Q plus R, will be either +2 or -2, and then we don't know the value of S, but S can be either only +1 or -1. So the entire combination, or this value, can be either +1, +2 or -2, and then this one is 0 when they are the same. So the entire value can be only +2 or -2. What happens if they are different? Yeah, then again, if they are different, the first term is 0, so we should only consider the second term. And then when they are different, the R minus Q will be either +2 or -2. And then again, T can be either +1 or -1. So the combination of these can be either +2 or -2. So again, whether they are the same or different, the value of these can be only either +2 or -2. And then there are 16 different combinations. So each of the case, it can be +2 or -2. And then what is the maximum value you can expect for this kind of expression? If we assume extreme case that this value will be always +2, in that case, the summation of then this can be factored out, but then the remaining part will be the summation of all the probability, which means 1. So even in the extreme case, the maximum value of this one can be +2. And then also if this was constantly -2, then it will be all added up, but the maximum value will be -2. So what I can claim is that the absolute value of S can be never larger than 2. So that's the inequality we can obtain for the local hidden variable case. So now what I'm going to do in the next page is that I will prove that I will show that for the entangled quantum entangled case, we can have S value larger than 2. And then if you actually if you actually implement this kind of experiment in real life, and then if you can obtain the value as larger than 2, then you can claim that this inequality is violated, and therefore we can say that this kind of local hidden variable theory is incorrect, or it is not valid anymore. To show that in quantum theory, or if the quantum theory is correct, then to show that we can violate the appearance inequality, then we should be able to calculate the prediction by the quantum theory. So how can we find out the prediction in the quantum theory? Well, for the quantum for the state generated by Charlie, we are assuming that Charlie can generate this kind of one of the pair basis type or the entangled state. And then how can we determine the probability? If you remember the statement for the third postulate, the way Copenhagen interpretation says was that for each of the measurement type, there will be also corresponding Hermitian type operator, measurement operator. And because it is a Hermitian operator, it will have orthonormal eigenvectors. And then we can use those eigenvectors as a basis vector. And then for any given quantum state, we can always expand given a quantum state in terms of the eigenvector basis. And then once we expanded that given quantum state in terms of the eigenbasis, then the coefficient, or we call it as the probability amplitude in front of the basis corresponds to the, and then for that value, if we square them, then we should first calculate the absolute value and then square them. Then it will be the probability. So the challenge we have to do is we should expand any of the given quantum state in terms of the eigenbasis for the measurement. And then now we have to consider what do we mean by measurement in this scenario. So in this case, I said that Alice can either choose Q type of basis, or Q basis corresponding to alpha equals 0, or R basis corresponding to alpha equals pi over 4. And similarly, for Bob's case, Bob can choose either S basis, which means beta is pi over 8, or T basis, where beta is 3 pi over 8 type. So these were the case, and especially we should calculate the probability for each measurement result case. What I mean by that is, for example, Alice chose the R basis, then we know that the measurement in the R basis can also produce either plus or minus value, or meaning that +1 or -1. And similarly, for the measurement in the S basis can generate either +1 or -1 value. So and then for this case, let's assume that let me find out if I want to find out the probability to measure +1 for Alice in R basis, and then -1 in S spaces on the top side. Yeah, so that is one probability we should find out. And then, of course, we should also find out all other combinations like a +1 or -1 +1 and so forth. So there will be 4 different cases, and then we should find out 4 different cases separately, and then finally we should obtain the expectation value. We have to multiply the given um, the calculated probability and the expected result of the, meaning the product of R and S value. So before that, yeah, let me review what then yeah then let me yeah so based on such kind of argument, one thing we did in the past was if I'm given this type of the integral state, my question was what will be the probability to measure the measure on yes and then if each of the photon is given to one of the photon is given to Alice and the another photon is given to Bob, then what is the probability that the Alice will measure diagonal value, diagonal polarization, while the Bob will measure the anti-diagonal polarization. Then to find out, what we did was we first converted or we first found out the relation between the HV basis and in terms of the TA basis, and then we replaced replace all these HV vectors with this type of expansion. And then finally, by expanding all these products, then and then we cancel if we cancel some of the canceling part, and then consider all those constructive and destructive interference, then we will be left with this final statement, final state. And then again, if I was interested in measuring the D for A, and then entire diagonal T basis for A, and then entire diagonal for Bob, then that kind of basis corresponds to here. And then based on that one, of course, I should not forget this global factor. So this minus 1 over square root of 2 is the probability amplitude in front of TA basis, and then I have to calculate the absolute value and the square, and then which is the half is the probability to measure the diagonal on the Alice side and the entire diagonal on the Bob side. So that's one way, but this sounds a little bit inefficient because we have to expand the entire state in terms of the T and A basis. So another way we can do is we know that this coefficient can be actually obtained by calculating, finding out the inner product between D for A and entire diagonal for B, and then we have to take the inner product between the between these spaces and the psi. And then if I apply this one to on this one, then we know that when this one is applied applied on multiplied to this one, then TA relation can be obtained by this coefficient, and then AV value. Yes, so if I just calculate as an example, then the TA AT multiplied on the psi minus corresponds to D A H A and A T, sorry, not T B, and then the VB, and so that was the this is multiplying on the first term, and then for the second term, it will be T A V A and AB and HB, like this one. And then the overall factor was the square root of 2. Yeah, so something like this one. And then this value can be obtained by this coefficient, and then also this one, A multiplied by V is also obtained by minus 1 over square root of 2, and so forth. So you can just immediately find out the coefficient. And then coefficient is not the probability. Yeah, never get confused. We have to actually then take the absolute value of this part. Yeah, so I have to calculate the. Oops, well, I should still have that cat notation. Then I have to calculate the absolute value and take the square, and then that is a probability. So if I summarize such kind of situation, then I can also claim in this way. So remember that in third postulate, if the particle is in the state, some kind of quantum state represented by vector in some vector space, then there will be always some operator corresponding to the measurement, and then the this operator is because Hamiltonian, Hermitian. It will have the orthonormal eigenvectors, and then each of the eigenvector will have the corresponding eigenvalues. So and then the probability to measure these eigenvalues as the measurement result is that I should calculate the inner product between the quantum state and the basis, eigenvector basis. And then yeah, eventually it should be calculated as the square of the absolute value, like this one. So for this specific example, yeah, so here, yeah, my example was, what is the probability to measure if the Alice want to measure in D basis? What is the probability for Alice to measure a diagonal value, while the Bob will measure the entire diagonal value? Then yeah, it can be obtained in this way. However, this example is not the same basis. Here, you know, maybe you can say that the R basis is maybe a TA basis. So yeah, in this case, we want to measure +1 corresponding to this vector, while for the Bob's case, it is not TA basis, but it is S basis, which is tilted by pi over 8. And then in this case, we were interested in measuring the -1. So if I write down the basis in on the Alice's side, and then in R basis, if I want to measure the in R basis, I'm interested in the probability to measure +1 on the Alice, and then -1 on the Bob side. Then yeah, we should be able to write down this kind of basis factor. And then all we have to do is to find out the probability to measure this kind of result is just to take the inner product between this vector and then psi. Then based on the previous argument, yeah, we can claim that to find out the probability to measure plus for the for some specific value basis, and then another +1 for another specific basis. Then what we have to do is calculate the inner product between the psi minus and the tensor product of the plus basis vector, tensor producted with another plus basis vector, which is represented as a plus of b. Then what I have to do, yeah, so I just replace this expression with with this one. Yeah, so yeah, this is the result. Then how can I calculate this one? It's actually quite straightforward, because for the first term, yeah, we have to do is multiply this one to entire vector, and here the h sub a is applied to the entire part on here, and then we know that HH will become 1, but HV will be 0. So so for the first term, I will just obtain the cosine alpha, and then for the second part, this will be multiplied the entire part, but again, VH will be 0, so VV will be 1. So I will obtain the sine beta. So the first term should become cosine alpha times sine beta. What about the second term? It is the same, similar. So yeah, in this case, the second term, yeah, including the minus sign. So we will just keep the minus sign here. But if the v sub a is multiplied, then it is multiplied only with this part. So VA will just this will cancel, and then only this term will survive. So we have sine alpha, and then the HB will be multiplied on the second part, and then because H will survive 1, and then we will have this cosine beta, but HV will become 0. So this term will go away, and then we will only have the cosine beta. And that's why we have cosine beta here. So that's how we can obtain the probability amplitude, not the probability. Yeah, yeah, that's how we can calculate the probability amplitude to measure the +1 in the on the Alice's side, and then +1 on the Bob's side. And then yeah, we know that based on the trigonometric identity, yeah, we can simplify the this kind of expression. Then what happens if I want to find out the probability amplitude for -1 instead of the +1 for the Alice's side? Then we know that here, yeah, the second case, we are interested in the measurement probability amplitude along this vector instead of this vector. And then the expression between these two are different only by the fact that instead of having alpha here, if I replace by minus pi over 2 minus alpha, yeah, the reason we have the minus sign is because it is here I'm just showing the magnitude, but because it is opposite sign, opposite direction, so I have to have the minus sign here. So that's why, and then if I replace this alpha with the alpha minus pi over 2, then yeah, you will obtain this kind of expression. So instead of using this one, I can just, all I can do is just replace the alpha in this expression with this one. So if I just do that, then I can immediately also get this expression. And then similarly for the um, Bob's side, for -1, yeah, if I'm interested in the probability amplitude to measure +1 on the Alice side and the -1 on the Bob side, then all I have to do is replace beta with the minus of this part. Yeah, so this is the absolute value or the positive value, but yeah, because it is on the opposite side, so I should have the minus overall. And then that corresponds to beta minus pi over 2. Yeah, so I just replace the beta with the beta minus pi over 2, and then we will obtain this kind of expression. Finally, for minus 1 case, yeah, we have to replace alpha with this one and the beta with the beta minus pi over 2, and we will obtain this expression. So now what I got is the probability amplitude, not the probability. So I have the probability amplitude to measure +1 +1, -1 +1, +1 -1 -1 -1. Then how can I obtain the calculate the expectation value? Well, expectation value is the summation of all the product of the value multiplied by the probability. So for the expectation value, for the first case, which is the +1, we know that the product of the RS is the +1. So here I didn't have any sign, implying the plus sign, and then this is the internal part is the probability amplitude, which I obtained here, but I have to calculate the square of the absolute value, so that's why I have this one. And for the second case, I can just calculate the probability square of the absolute value, but I have to have keep the minus sign in front of it, because here I'm assuming that R is -1 and then S is +1. So the product of RS value is the -1. And for the third case, it is the case. So I have -1. And the fourth case, -1 minus 1 multiplied, they will become +1. So that's why I have this +1. So this is kind of a value we are expecting. And then the part inside the inside this absolute value part corresponds to the probability. So if I just replace all those expressions, then this is a simple algebra. So if you work out the details, then you will actually obtain this expression. Now, from the previous page, I obtained this kind of expression for the angle alpha and beta for Alice and Bob's case. And then this is the expression. But that was not the only result we were looking for, because eventually we want to compare the result between the quantum theory and then the hidden variable theory. And then for the hidden variable theory, what we actually calculated was the S value, which was defined in this fashion. So now what I just obtained here was corresponds to only this case, or only one of these case, but it was general enough so that I can just, by replacing the alpha and beta with the corresponding angle, then I can just obtain the each of the expectation value immediately. So now alpha, so QS corresponds to QS means that the alpha is 0, because this is HV basis, while for the S is the basis which is tilted by beta equals pi over 8 from the horizontal axis. So beta is just pi over 8. So all I have to do is just replace alpha and beta with the 0 and pi over 8. And then for RS, similarly, R is tilted by, for the R basis means the alpha is tilted by pi over 4, and then the beta is pi over 8. And so just to replace, and then for the other cases, I just have to repeat the same thing. So for these cases, I have the direct result or expression. So I just plug in alpha minus beta, then I will just obtain this result. And then for the last term, it is the same formula, but now I have to, if I calculate the alpha minus beta, meaning the minus 3 pi over 8, and then the and then I have to I should not forget the factor of 2. So then I will have this expression, and then this is immediately calculated. And then if we just add all of these together, I have the typo here. So it is less than -2, meaning that the absolute value of S is larger than 2. So here, what I want you to say was the absolute value is larger than 2. So it is, and then yes, because now this Bell inequality, initially based on the based on the hidden variable argument, the absolute value of S was supposed to be equal to or less than 2. However, in this case, we obtained the result that S is, the absolute value of S is larger than 2. So in experiment, if we can prove that the absolute value of this guy is larger than 2, then we can rule out the hidden variable theory. Only at least the hidden variable theory we assumed at the beginning in today's lecture. And then in experiment, people actually all the experiment up to now all prove that S is larger than 2. And I also did a similar experiment in my when I was a graduate student. So there is no doubt that this S value balancing inequality is violated all the time. And then again, there are many different forms of the balancing inequality, and then the way it is written as called as CHSH form. Then the next question is, how is this related to the QKD, quantum key distribution? So the protocol which uses integral state, for the QKD is called as E91 protocol, and the reason is it was developed by the Arthur Eckert in 1991. And then the here, if you remember the CHSH measurement, we were using this kind of basis for on the Alice side, and then for the Bob side, we are using this basis. And here, because there is no matching basis, meaning that the same basis are used for Alice and Bob, actually there is no correlated result in general. So but the goal of the quantum key distribution is to generate the reliable secret key. So, and then such kind of reliable secret key can be only generated when Alice and Bob uses the same basis. So E91 protocol still uses the concept of the CHSH, but it actually added 2 more bases on the Alice, one base, additional basis on the Alice side, and then the additional basis on the Bob side. And then by doing this, we know that, and then Alice will randomly choose one basis out of these 3 possibilities, and then Bob will also randomly choose one basis out of these 3 bases. So there will be 9 different combinations of the choices on the Alice and Bob. But when the Alice chooses the pi over 4, and then Bob also chooses the pi over 4 simultaneously, then they are using the same basis. So in principle, the resulting measurement result should show the anti-correlation relation, which I already mentioned early in one of the early lectures. And then also, if Alice and Bob chooses the same pi over 8 basis, then they will also have another anti-correlated result. So when Alice and Bob uses the same basis, then they will actually generate the reliable quantum key, secret key. While if they choose the different combination, then actually they are not useful for the key generation. Then why do we actually use more than necessary? Well, the reason is if we don't choose the matching case, then what we can do is, instead of throwing away all those unmatching cases, we can use those data for the purpose of the CHSH measurement. Then why do we try to measure the CHSH measurement? Well, if you remember the goal of the QKD, it is we want to make sure that only Alice and Bob shares the same secret key, and no one else can have the secret key. And then the question is, how can Alice and Bob trust Charlie? Charlie might be the two people might consider the third guy, Charlie, as a trustable people, but maybe Charlie might be compromised, and then Charlie might actually work as an eavesdropper. In that case, Alice and Bob don't want to trust Charlie. So they want to make sure that Charlie will always generate the correct correct entangled state. So if the Charlie intentionally distort this state, and then he just intentionally send some known quantum state for both of them, then because Alice and Bob will mix the measurement basis, and then Bob will also randomly choose the basis. So whenever they do not, whenever their choices do not match each other, then they can use the remaining data to verify that the 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 state sent generated by Charlie is really the psi minus, and then if they just measure the CHSH measurement, and then the value does not violate the classic the hidden variable limit or classical limit, then they might suspect that Charlie is compromised, and then they do not use the key generated during some period, and then they will just discard those secret key, and then either ask Charlie to send the correct quantum state, or they will replace the Charlie. So by using the um, um, yeah, so and then also, yeah, even if there is any kind of eavesdropper, then the calculation of the CHSH value won't reach the this kind of square root of 2 type of value. So yeah, again, yeah, they might suspect that there was some kind of problem during the transmission, and then they will just discard all those keys. So that's actually in some sense maybe safer, or uh, compared to the BB84, because now they can always confirm that this is always guaranteed. And then the more advantage compared to the BB84 is that the typical BB84 only send out the single photon, and then if the single photon cannot go any further, then they should use the so-called as a trusted repeater. However, trusted repeater is not necessarily trustable. Yeah, so yeah, that is already a digital device. So digital device can be always hacked in principle. So how can we guarantee the safety of the or security of the entire system? And then instead of using the PB84, if we can distribute the entangled state over a very long distance, and then I already showed you that they can be delayed by using the quantum repeater, using the with the entangled state again, then the entanglement can be created over very long distance. So in that case, Alice and Bob can safely confirm that the entangled state is pure, or it is not compromised by some eavesdropper, and then they can still generate the new keys whenever these two bases match to each other. So yeah, so that was introduction for the E91 protocol. And then more interesting result was recently published a few years ago. And then in this case, as I mentioned in early lectures, yeah, they actually put the entangled photons pair generator on the satellite, and then they distributed two photons on the separated station on the Earth. And then and then I mentioned that they used what I developed in the past. And then so um, yeah, so and then with that entangled photon pair generator, they actually did CHSH measurement. So this is exactly the form of the CHSH measurement I just showed you. And then in that case, their measured S value was the 2.37, which was much larger than 2. So in principle, they can confirm that their generated photons are entangled over a long distance. And then in this case, they can say that they can use this entangled pair for the purpose of the quantum key distribution. So people sometimes ask the meaning of this experiment, and then the first meaning of this experiment is that they actually confirm that the entangled state still is maintained over very long distance, like 1,200 kilometers, which is a huge distance. And then still the concept of the quantum entangled state is valid. And then another implication is that in principle, people can use this kind of scheme to distribute the secret key over a long distance. Of course, there is also a limitation because this means that only the satellite can cover the entire globe, but it is not possible. But yeah, people also consider that there will be another satellite, so they will relay the photon between the satellite or something like that. So that's the meaning of the this experiment. And then I think many of you actually saw the news article about this kind of experiment. And then sometimes, as I kept emphasizing, this doesn't mean that communication can be done faster than speed of light. Yeah, this has nothing to do with communication. It is about the distribution of the entangled state. And then and it is actually the scientific experiment to verify that the first goal of this experiment was to verify that the entangled state, the concept of entangled state is still valid for a very long distance. Okay, so I will stop today's lecture here, and then we will continue in the next lecture.